So the wave nature of light has been established, and it's a straightforward idea. There is nothing vague about this. However, it was not able to explain all the phenomena associated with light. One of the unexplained phenomena based on the wave nature of light is called the black body radiation. It's basically the fact that when you heat up something to high temperature, it is gonna emit light of all frequency. An example for that is the sun. Sun is just a very hot body, and that's why it emits a wide spectrum of frequencies. Based on the wave nature of light, if you try to explain the relationship between the intensity of emitted light with increasing frequency, you will find that it should be exponentially increasing according to the relationship intensity proportional to the cube of the frequency. However, what we see, what we experimentally observe, is that the intensity increases and has a maximum, then it decreases again. So that classical description of light as a wave is not able to explain this phenomenon. The only successful explanation for this phenomena was done by Planck by introducing the concept of quantization of light. What he said is that intensity of light is proportional to two terms. Classical term is the same based on the wave nature of light, and then we have a quantum term based on the postulate that light moves in whole packets of waves called photons, with energy of each photon proportional to frequency, and the proportionality constant is called Planck's constant. That was a very revolutionary idea. It was actually very successful in explaining this phenomena right here, because if you plot this equation, you will get a matching curve with the experimental curve, where at low frequencies, the classical term is going to be the one dominating. And then when you go to higher frequency, classical term is going to diminish and the quantum term of the equation is going to kick in and is going to make it match with the experimentally measured black body radiation. And it introduced a revolutionary idea that light is not just a continuous wave as classical physics suggests. It's actually discrete quanta. Quantum stands for a whole thing, discrete whole things called photons with energy that is only proportional to frequency with a proportionality constant that equals this value right here. That was a really revolutionary idea that led to the development of the quantum mechanics or the quantum description of the atom, what we will discuss in details later on. So based on this idea, light is a wave. It's an electromagnetic radiation, a wave in both the electric field and the magnetic field around us, with an energy that is directly proportional to frequency, inversely proportional to wavelengths, and directly proportional to wave number. So based on that, we can actually draw a spectrum on a scale that describes the different regions of the frequency. So the frequency and energy will be directly proportional to each other. As you go to higher frequency, the energy associated with the light photon is going to be higher, and same relationship is between wave number and energy. As you go to larger wave number, you're increasing the associated energy as well, while the wavelengths is inversely proportional. So longer wavelengths means smaller energies, shorter wavelengths means higher energies. And the whole region of visible light lies in this small region right here within the range of wavelengths of 400 nanometer to 700 nanometer. So just to emphasize the relationship between energy and wavelengths, we will calculate the energy associated with two photons in two different regions in the spectrum, infrared region and X-ray region. So if you want to calculate the energy associated with a certain wavelength, you will basically use the formula E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. So it's going to equal 6.63 times 10 to a negative 34 joule second, multiplied by 3 times 10 to the power 8 meter per second, divided by the wavelengths, but it has to be converted to meter. So it's going to be 5.00 times 10 to the power 4 for the first photon, nanometer. Then you have to multiply this times the conversion factor from nanometer to a meter, which is 10 to a negative 9. So you carry out this calculation. The nanometer will cancel out with nanometer, meter will cancel out with meter, second will cancel out with second, and you will be left with a quantity in joules, which is the unit for energy as we know, which is going to give you 3.98 times 10 to a negative 19 joules. So you repeat the same type of calculation for the second photon in the X-ray region using the same formula. It's going to be E equals Planck's constant, which is 6.63 times 10 to a negative 34 joule second, times the speed of light, which is 3 times 10 to the power 8 meter per second, divided by the wavelength after you convert it to meter, which is going to be 5.00 times 10 to negative 2 nanometer times the conversion factor from nanometer to a meter, which is 10 to the negative 9. And carry out the calculation. It should give you basically the same base, which is 3.98 times 10 to negative 15 joules. And it's clear that the energy associated with the X-ray photon is much higher in magnitude than the energy associated with the longer wavelength photon of the infrared region. As we expected, energy is inversely proportional to wavelengths. So longer wavelengths will have smaller energies, shorter wavelengths will have larger energies.